Here is a question we are tasked with. Using the thermodynamic potentials, derive the Maxwell's relations. So we need to bring out the thermodynamic potentials. What are they? Now, if you have not actually gone through that video, I've actually linked it to this video in the description section. So feel free to go check that out. And if you have gone through that, and we can move on. So this is going to be the first one. You have du, and du is equal to TdS minus PdV. The second one is going to be dH, and that is going to be TdS plus VdP. That is the change in the enthalpy. And the third one is a change in the Helmholtz function. That is minus PdV minus S dt. And the fourth one is a change in the Gibbs free energy. That will be VdP plus S dt. So this is a first group of equations that you would actually need to derive the Maxwell's relations. Now we also need some functions to do this. That could pretty much be found from the thermodynamic potentials. From this first off, we can find that the change in the internal energy does actually depend on the change in the entropy as well as the volume. So that is going to make the internal energy from here to be a function of the entropy as well as the volume. Now going on to the second, we have dH such that the enthalpy is a function of the entropy and the pressure. And for the third, we have that F, which is a Helmholtz function that depends on V and T. And for the last one, we have G. G will depend on P and T. So we're going to start with the first equation. So from the first thermodynamic potential equation, we have that du, that is equal to TdS minus PdV. Now, let us say this is equation 1. We also know that u is a function of S and V. So let us find out the natural derivative of u. That could also be called as a total derivative. That will be the partial derivative of u with respect to S at constant V multiplied by natural S plus the partial derivative of u with respect to V in this case, and that is not going to be at constant S multiplied by the natural form of V. And let us say this is equation 2. Now if you looked at this, you would find that we have a dV for the last term on the right hand side. We also have a dV on the side. So that makes P to be equal to this stuff. Now on this side we have a ds also, and there is also a ds from the first. So that makes T to be equal to these other stuff. So let us start with the first. We have under comparison, I'm just going to write that here, comparing. That is comparing between equation 1 and equation 2. We have that T is equal to partial U, partial S at constant V. Now this form, we're actually going to differentiate this form with respect to V at constant S. What does that mean? We already had this as a derivative with respect to S. So in this case, we had S to be the variable and V was the constant. Now we're going to differentiate it in the form that V would be the variable and S would be the constant. So I might well write it here. Differentiating with respect to V, keeping S constant. So that is basically what we need to do. We need to make S constant. So we are keeping S constant. And what is that going to give? We would have partial t, partial v, and that is our constant S. And this is going to be equal to partial with respect to v of this stuff. That is partial u, partial s, our constant v. We already had this stuff on the right hand side. So we need to differentiate it with respect to v, and that will be at constant s. So that is going to be an s over here. Now I could well join up these whole forms. These are actually two functions. So I'm going to take this d and multiply it with d du, and that is going to be d squared u, and that is divided by, let me take this out, that is divided by dv multiplied by ds. Let us say this is equation star. So we have that t, whoa, I don't need to show that, partial t rather, partial v with respect to s, that is equal to d squared u of dv ds. So as we said, this is equation star. Now next up, we're going to compare the other side of the equation, this side. Now we had initially that du, that is equal to tds minus pdv. So since we have a dv here, we're going to see that negative p is equal to du dv at constant s. So that is what we need to use in this case. So I'm going to take this arrow out, and we're going to say that negative p is equal to partial u partial v with respect to s. So I'm going to wipe everything out from here. Now, as you know, we need to differentiate both sides with respect to s in this case and at constant v as usual. So this is going to be a negative, that will be a partial p with respect to s, and this in this case we're going to have a constant v, and this is going to be a d with respect to s, and that is multiplied by du dv, which was at constant s. Now we know this should be the derivative of this form with respect to s at constant v. So I'm going to write that here. They should be at constant v. So I will take this out. Now this is going to be d squared u divided by ds dv. So that is what you have right there. I'm going to call this as equation 2. Now, if you notice, we have that d squared u dv ds. That is the same thing as d squared u ds dv, right? So since we have this to be, that means what is on the left hand side of both equations are also going to be equal. So therefore, we have that dt dv at constant s, that is equal to negative dp ds at constant v. So this will be the first Maxwell's relation. Now let us try to find out the other ones. So the next thermodynamic potential that we need to use, we're going to use dH. dH is equal to TdS plus VdP. Now what this means is the hydrogen, whoa, this is not a hydrogen. This is the symbol for enthalpy. Please do not be confused. We have H, and that depends on the entropy and the pressure. So we need to work the natural derivative of this function. That is going to be dH, and here we're going to have the partial derivative of H with respect to S at constant p multiplied by the natural s plus partial h partial p at constant s multiplied by natural p. So whilst this is equation 1, this is going to be equation 2. Now we need to compare it as usual. Here now we're going to have that t is equal to this stuff. So the first one we have that t is equal to partial h partial s at constant p. So what we need to do, we actually need to differentiate both sides, this time with respect to the pressure, and we're going to keep the entropy as a constant. So that will be partial t partial p at constant s, and that would work this side also. Partial p. So I'm going to write it this way, and we're going to have the stuff which will be differentiated. It is this. We know that this derivative should work at partial s. And let us multiply everything. We're going to have a d squared h that is divided by dp ds. We have the derivative of both functions, so there is not going to be any constant right there. So that is what we have for the first. And we now have for the second that we are going to have a v is equal to partial h partial p at constant s. So that is going to give us, well, let me rewrite it. This is partial h partial p at constant s. Now we need to differentiate both sides now with respect to s at constant p. So that is going to be partial v partial s at constant p, and here we're going to have partial s. You know, this must be at constant p. Now we need to differentiate what was already on the right hand side, and this is with respect to p. So as usual, this is going to be d squared h, and this is divided by dp. Let me write it in chronological order. So this is ds dp. So that is what you're going to have. Now we already know that this is the same thing as this, so that is going to make this to be the same thing as that. So you're going to see, since we have this to be equal to this, that means we have that this is equal to this. So we have a partial v partial s at constant p that is equal to partial t partial p at constant s. This will be the second Maxwell's relation. Now let us jump into the third one. So we need a third thermodynamic potential. That is the Helmholtz function. That is equal to minus p dv minus s dt. Now from here you can figure it out. The Helmholtz function is a function of the volume as well as the temperature. So the natural derivative of that is going to be partial f partial v, and this will be at constant t multiplied by the natural of v plus partial f partial t at constant v multiplied by natural t. So from here we can find it to be that we got a negative p, and that is equal to the partial f with respect to partial v, or with respect to v rather, and that is at constant t. So right now we need to differentiate both sides with respect to t, and we're going to keep the volume constant. So this will be minus partial p partial t, keeping v constant, and on this side we're going to have the same thing. This is partial t, and we're actually working on this stuff. that is df dv at constant t. Now we know that what we were working is actually in terms of a, well, that is at constant v rather. So we have a constant t, a constant v, which all cancel out, and this gives us a d squared f divided by dt plus dv. So this, as usual, we might well call it as equation star. And so let me wipe this stuff out. Now from here, what we're going to say, well, I might well need to take that back. We can see that we have a dt as well as another dt right there. So here we can say that negative s is equal to partial f partial t at constant v. So I can wipe it out now. I'm going to wipe these out also. So we have this working. Now, as you know, we need to differentiate both sides with respect to v, and now we're going to keep t constant. So that will be negative partial s partial v with respect to t. So this is going to be partial v, and that is with this function, partial f partial t at constant v. And what we were doing must be at constant t. So we know this should become d squared f divided by dv multiplied by dt. So that is what you have. And here we're going to call this equation star star. Now, as you can see, we have these two stuff to be equal. So that is going to make this and this as the same thing. So we have that negative partial s partial d or partial v with respect to v is equal to negative partial p partial t with respect to v. Now we know that these guys can get canceled out. So that's going to go out. This is going to go. And so that is what you're going to find. So this will be the third Maxwell's relation. Now let us go over to the fourth and the last. So that corresponds to the Gibbs energy. We have Gibbs dg, that is equal to vdp. So this is actually minus vdp minus sdt. Now we know that the Gibbs free energy will therefore be a function of the pressure as well as the temperature. So differentiating naturally, we're going to take the partial derivatives of the Gibbs energy with respect to both constants. No, with respect to both functions. So this is going to be partial g, partial p with respect to t with natural p. And here we're going to have a partial g, partial t with respect to p multiplied by natural t. Now we have that v is equal to partial g, partial p at constant t. So as you know, this stuff should change to a partial v partial t at constant p in this case. And here we're going to have d squared g, and we're going to have dv dp in it. So let us say this is equation star. Now over here we have that negative s is equal to dg dt at constant p. Now we can actually find out what will be the derivative of this entropy with respect to pressure at constant temperature. So that will be minus partial s partial p at constant t. And here we're going to have d squared g. And this will be dp dt. So here this will be equation star star. So we already know everything works. We know that this is the same thing as this stuff. So that makes the whole stuff simpler for us. So therefore we're going to say that partial V partial T at constant P is equal to negative partial S partial P at constant T. So this will be the last Maxwell's relations. So that is basically it. By now, hopefully you know how to derive all the Maxwell's relations from the top of your head. You just need to bring out the thermodynamic potentials and use them to derive the functions which are actually needed and the variables which they all depend upon. And that will be basically it.